In our last adventures in graph theory, we were looking at Euler paths and Euler circuits where you had to use each edge exactly one time in a graph. Today we're going to look at Hamilton paths and Hamilton circuits where you have to use each vertex exactly one time, with the exception of a circuit where the beginning and ending vertex is the same one. So these are named not for Alexander Hamilton, as in the famous musical by Lin-Manuel Miranda, but for Sir William Rowan Hamilton, a whole different person. He was an Irish mathematician and astronomer in the 19th century. He had work involved the use of quaternions in abstract algebra. In fact, he was working on problems with those and was on a walk with his wife when he was able to puzzle out something about them, and immediately was like excited and had to carve the solution, had to get it written down, was going to burst, had to write it down. He carved the solutions of his puzzle of how to multiply quaternions in the Brougham Bridge. And if you decide to be a tourist today and go visit that same bridge, you can see his carving on the bridge still. It is still there. He was friends with the poet William Wordsworth. You might have heard of that poet in your English classes. And he invented something called the Acasian game, which if you look in your current textbook, if we're still using a survey of mathematics, they have in one of the homework problems a picture of that game so you can see what it looks like. It's actually a little board game. Okay, so back to Hamilton paths, Hamilton circuits. Again, Hamilton path is a path that passes through each vertex of a graph exactly once. This will come in handy when we're trying to look at routes for things, because certain routes you have to make certain stops. So you have to go to these vertices, these stops. Hamilton circuit is a Hamilton path that begins and ends with the same vertex. Okay, for example, let's say you have a graph that looks like this. With vertices A, B, C, D. We have an edge between B, D. We have an edge between CA, we have an edge between BC, an edge between CD, an edge between BA, and an edge between AD. Okay, so there's our graph. And we're interested in some Hamilton paths or circuits. So some examples of some Hamilton paths. Let's see. Let's say we start with A. You can go to B, to C, to D. And if you stop there, that's a Hamilton path. Or if you go all the way around, you can have a Hamilton circuit. So in purple, if we continue on, you can have A to B to C to D to A. And you could do variations of that, like you start with B and go C, D, A, B or something, or you could go the other direction. You could go A, D, C, B, A. So all kinds of possibilities, but the focus is on visiting each of those vertices one time. I'm going to use a different color. Let's say we started with C. You could go to A, go across. You could go up to B, and then go down to D. That would be a Hamilton path. That's an example of one. Or if you wanted to wrap that up, you could then continue back to C, because you started with C. So yeah, you could go back to C if you wanted to make it a circuit. C to A to B, B to D, D back to C. And notice you don't have to use every edge on these. Euler circuits and paths, you had to use the edges. Hamilton paths and circuits, it's the vertices you're focused on. And you're not going to use an edge. Usually you're not going to use an edge more than once, but you definitely, the vertices, you have to use those exactly one time each. But you can skip edges. So notice that on the green one, I didn't use the edge between A and D, or I didn't use the edge between B and C. So that's possibilities too. Okay, that graph was not an example of a complete graph. A complete graph is a graph that has exactly one edge between each pair of vertices. Every complete graph has a Hamilton circuit. So the question is, how many unique Hamilton circuits are in each complete graph? And we're going to answer that. But first, let's just look at what complete graphs look like. One example of a complete graph, like if you've got 3 vertices, you're going to have an edge between each pair. So in this case, you're going to have 3 edges. That's a complete graph. Let's say you have 4 vertices. You have to have an edge between each pair. See, that's not all, because you also have this pair and this pair. So notice in that you have 6 edges. Let's see, 5 vertices. It's going to make a nice pentagram. Once you put edges between each pair of vertices, you end up with 10 edges. Let's say you have 6 vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's already there. 13, 14. Over here, 15. And that looks like that's it. So 15 edges. Some of you might be noticing there's a bit of a pattern to this, actually. 1, 2, 3, 4, 5, 6, 7. 7 vertices. I'll probably stop after 7. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and that appears to be it there. I'm going to stop with that, and I'm going to revisit what's happening here. Look for a pattern. Let's see. Notice that. All right, I had 3, 3. So for vertices and edges, let's see what we got here. Vertices, edges. 3 vertices, 3 edges. Then we had 4, 6, 5, 10. Then we had 6, 15, and 7, 21. And I wonder if you could spot maybe a pattern to figure out, well, what if there were 8 vertices or 9 vertices or 10 vertices? How many edges are there going to be? Well, it appears when you look at the vertices each went up by 1 in that column. Notice the edges kept going up by 1 more. Like 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 5 is 15, 15 plus 6 is 21. So I can figure out for 8 vertices, there's going to be 21 plus 7, or 28 edges. For 9 vertices, there's going to be 28 plus 8, or 36 edges. For 10 vertices, 36 plus 9, or 45 edges. Start to end up with a lot of edges. It's kind of cool looking. If you're into that kind of art, it's kind of cool if you can do a lot of, it's like do a drawing with a lot of sides. What if we don't know the number, like what if we just want to come up with a generic formula for n vertices? I wonder what the relationship is with the number of edges. Let's see here. Each each time you took the previous number, whatever it was, and then added one number higher. So I mean, if there were such thing as two vertices or one vertex, then the idea then would be two vertices. You should be able to subtract 3 and 2 and get 1. And then you should be able to subtract 1 and 1 and get 0, right? Like 0 plus 1 is 1, 1 plus 2 is 3, and so on. You're just trying to figure out a pattern here. Like we start out like with n vertices and then n minus 1 edges, n plus 1 vertices. Then you took n minus 1 and added 1 to it and got n. So n plus 2 was then n plus 1. N plus 3 was then n plus 2. Nope, that's not quite it. I like trying to think about what patterns there are. This is an example of number theory. When number theorists are working on proofs, they like to start looking at patterns. They like to use n's to do a generic representation of what's going on. Well, you're always taking the previous number and adding one less than what the number of vertices is. You could look at it too. Let's see, or it might not be an addition problem. Like if n is your number of vertices, let's see, what if we multiplied 4 times 1 less, that's 12. Well, 12 divided by 2 would give you 6. And what if you did multiply, instead of adding, what if you thought about as multiplying? 5 times 4 divided by 2. Well, that's 10. 6 times 5 divided by 2, that's 15. Oh, 7 times 6 divided by 2, that's 21. That works. So if you took whatever the number of vertices is, times 1 less than that, you could divide by 2, get the number of edges. So there's a bit of a pattern right there. Nice little tidy formula. So you could always see that relationship no matter. So then if you said, oh, there's 100 vertices, then you could say, well, that means there's 100 times 99 divided by 2 edges. So like 100 over 2 is 50. 50 times 99, 0. 45, what, 49? 49, 50? Let me double check. 100 times 99 divided by 2. Yep, 4,950. So then I was able to use that formula to see, well, if I have 100 vertices, I'm going to have 4,950 edges. I'm not going to ask you to draw something like that. That would take all day. But pretty cool, huh? All right. What if now, instead of just looking at edges, what if we start looking at our Hamilton circuits involved with this? Let's revisit our 3 vertices, and let's name that A, B, and C for the vertices. So that's a complete graph. Now we know about edges and vertices. Let's look at Hamilton circuits. Okay, let's first do a group that starts with A and ends with A. You got A to B to C back to A. Or you have the other direction, A to C to B, back to A. Those aren't the only possibilities. You could start with B. You could go B to A to C to B, or you could go B to C to A to B. That's one way you could do it. Or you could start with C, go C to A to B to C. Or you could go C to B to A to C. So you have 2 that start and end with each vertex for a total of 6. Interesting. Let's do one with 4 vertices. We're just talking complete graphs here. If it's not a complete graph, then you're going to have different numbers. You can still do Hamilton paths and circuits, just you might have different numbers of them. Let's name this L, M, N, and P. I don't like to use O because people mistake that for 0 sometimes. Let's do some Hamilton circuits there. We could do L to M to N to P to L. Or you could go backwards and do, well, you know what? I know I could go backwards and do L to P to N to M to L. Let me do it to the side because I like to do this in kind of a organized manner to help me keep track of where I've been and where I'm going. So I'm going to start with L and M again and just swap the P and N. And then over here, I'm going to start with P, L, and P again and swap the M and N. That's not backwards from there, but it's kind of a systematic way maybe of doing this. All right, what if I start with L and N first? Could go L, N, M, P, L. Or if I start with L, N, I could also go P to M to L. And that's all of my possibilities, isn't it? Because I either can start with LM or LN or LP. All right. So that's all starting with L. So there were 6 of those. Okay, what if I started with P? I could go P to L to M to N to P. Or I could start with P and L and switch the M and N. Or I could go P to M to L to N to P. Or I could be P, M, and switch the L and N. And then I could do P. I went P to L, P to M. I didn't go P to N. P to N to L to M to P. I can also do P to N to M to L to P. There's 6 of those. In fact, there's going to be a pattern to this. If there's 6 that start and end with L and 6 that start and end with P, there's also going to be 6 to start and end with, I'm running out of space, so I'm just going to stop it here. Start and end with M, and there's going to be 6 to start and end with N. So you're going to have 24 total there. 6 each. And there is, in fact, a mathematical pattern to this. I'm not going to have you try to discover it. I'm just going to go ahead and tell you. How many unique Hamilton circuits are in a complete graph anyway? For n vertices, the number is n factorial. That's what that little exclamation point means. In factorial reads, in exclamation point means in factorial. It means you take whatever the number is and multiply by the positive integers under it down to 1. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. That's what that means. And you should have a button on your calculator that does that for you. If you have a scientific calculator, your button might say x factorial or something like that, or it might say n factorial. Or you might have to go into a probability menu, a PRB menu, or a math menu and then PRB. It just depends on your calculator. But scientific or graphing will do factorial for you. For function will not. I mean, for function you could sit there and manually type in 5 times 4 times 3 times 2 times 1 and see what you get. So this is the number of Hamilton circuits in a complete graph. Each vertex will have one less than that factorial Hamilton circuits. So like earlier, we had 3 vertices. That was 3 factorial, 3 times 2 times 1, which is 6 total. And then it was 2 factorial, or 2 per vertex. When we had 4 vertices, that was 4 factorial, 4 times 3 times 2 times 1. So that's 24. And then 3 factorial, 3 times 2 times 1, or 6 per vertex. In your project, I'm going to have you guys do. You have that project where you have some questions concerning a U.S. map. You have to answer those with what you know about Euler paths and circuits and all that. Then you have take a dream vacation. And in the dream vacation, you're going to be dealing with Hamilton paths and circuits. Because in the dream vacation, I have you leave from home and visit 4 other places and then come back home. Of course, this is assuming we don't have coronavirus to worry about. Don't have COVID-19 to worry about. You're free to roam, free to go wherever. And you end up with drawing. You're going to end up drawing a complete graph of 5 vertices. And you're going to have to figure out all of your different possible Hamilton circuits, starting and ending with home. So on that complete graph with the 5 vertices, your complete graph's going to look like this. It's not going to be that pentagram one. And there's 5 factorial, or 120 total possible. But you only have to worry about starting and ending with 1 vertex. You don't have to do all the total possible. So you're just going to have to worry about 4 factorial, or 24 from 1 vertex. So there'll be 24 possible paths, starting Hamilton paths or Hamilton circuits, because you're going to start and end with home. Hamilton circuits from your home vertex. Yeah, so if you do your problem and you don't have that pentagram for your graph, then you're doing something wrong. And you should come up with 24 possible routes. And then that project too, if you've already looked at it, it also has a question about trees, which we'll get into in the next video. So don't worry about that just yet. But first part, you're going to be thinking about Euler. Second part, you're going to be thinking about taking a trip and using Hamilton. And then that third big part has to do with trees. Now, speaking of which, you really are going to be doing something called a traveling salesman problem. Graphs can help us represent geographic locations. The vertices can be locations. And then the edges can help us with figuring out how to travel between them. Traveling salesman problems work on finding the least expensive or the shortest route to take so that each location is visited exactly once before returning home. And there's a few methods you can use. One of them is brute force. And you're going to use all 3 of these methods in your project. The brute force will give you the optimum solution. this will find you the cheapest or the shortest. If you're cheapest if you're dealing with money, shortest if you're just dealing with distance, it will find you that route. But it is the longest method out there, because you have to sit there and make a complete weighted graph, list all possible circuits from your starting vertex, determine the cost or distance associated with each of those circuits, and choose the optimal solution after doing that. Just see which one's the lowest or cost or shortest distance. So this can be time consuming, but I got faith in you. You can do this. All right, so what is a weighted graph? A weighted graph is a graph where the edges are labeled with values. So in our case, like in your case, if you're planning a trip, you could like look up airfare, and then you could label your edges with the airfare between those two locations. Or if you're wanting to look at gas mileage or something like that, however you want to do it. I'm going to do a graph here that is not as big as the one you're going to do for your project. You're going to have 5 vertices. I'm only doing one with 4, just in the interest of demonstrating how this is done. I don't want to take up too much video time doing this. So I'm just going to have 4 vertices. But I'm going to go ahead and label the vertices with weights. Between A and B, it's going to have a weight of 10. B and C is going to have a weight of 18. C and D will have a weight of 13. A and D will have a weight of 14. All right, between A and C, that's going to have a weight of 15. And between B and D, that's going to have a weight of 16. All right, and let's say that A is home. Okay, so from home, let's list our Hamilton circuits. We could go A to B to C to D, back to A. Or we could go A to B to D to C, back to A. Wait, before I even go any further, that's 4 vertices. That means 4 factorial. 4 times 3 is 12. 12 times 2 is 24 total routes, or 3 factorial, which would be 6 per vertex. So I only need to worry about 6. All right, so I've got 2 so far. So, because I'm only starting it with just the one vertex A. Then I could go, instead of going to B first, I could go to C first. A to C to B to D to A. Or I could go A to C to D to B to A. Those are some possibilities. Or I could go A, instead of A to B or A to C, I could go A to D to B to C to A. Or I could go A to D to C to B to A. All right, so I just listed my 6 possible routes if A is my home. What I'm going to do next is use those weights on that weighted graph. And I'm going to decide my total. Those weights might be distances, that might be mileage. Notice these graphs aren't necessarily drawn to a scale. We're just doing a quick sketch here and getting some kind of a representation. All right, so for that first one I listed, A to B has a weight of 10 on it. B to C has a weight of 18. C to D has a weight of 13. And D back to A has a weight of 14. So you add those up, and you see what that comes out to. I think I'm going to get 55. Let me do it with my calculator just to make sure I don't make a mistake. I'm trying to do it in my head. Yes, that is 55. Okay, and I'm going to do that for each one. Now, honestly, I expect reverse to come out the same. So if A, B, C, D, A is 55, then the reverse, A, D, C, B, A, is also going to be 55. So that saves me some work. And on your project, you know, airfare from here to St. Louis might be different than airfare from St. Louis to here. don't worry about that. Just pick one number and stick with it. Don't worry about having different numbers in different directions. Just between two cities, pick a number, put that down, and that's what you work with. I'm not going to be sitting there and going over all of your travel data on as far as your graph goes. I'm going to be looking at your list of routes and whether your sums come out correctly and whether your graph was done correctly. I'm not going to go online and look up airfare and see if you did that part, if you got that part right. So, just pick a number and put it in there. Okay, airfare, gas mileage, whatever. I'm not going to go on a map and see if you measured the distance correctly between your locations. I am going to take whatever you give me for your weighted graph and make sure that everything else, all the other math's correct, though. All right, so then, let's see. All right, back to the second one, A to B to D to C to A. See, A to B, we know is 10. B to D is 16. D to C is 13. And C back to A is 15. I think that's 54, but let me plug it into my trusty machine here and make sure I didn't mess up. Yes, that is 54. And then the reverse, A, C, D, B, A will also be 54. So notice, like on your project, it sounded like a lot where you have to do a list of 24 routes. But really, you only have to do add up 12 of them, because then the exact reverse order is going to also come out the same. So, all right, A, C, B, D, A. A to C is 15. C to B is 18. B to D is 16. And D back to A is 14. 30, 49. I think I'm getting 63, but let me double check. 15 plus 18 plus 16 plus 14. Yes. So they're complete opposite. A to D to B to C to A will also be 63. All right, what am I going to do with that? Well, I'm going to look at what's the cheapest on there, the shortest, and I am seeing 54 as coming out the shortest. So my optimal route, A, B, D, C, A. Or A, C, D, B, A. Has the lowest at 54. So this is the optimal route. As you can see, though, this is kind of a time-consuming process. We only used 4 vertices. Your project's going to use 5. That's a little bit time-consuming. But can you imagine how much worse it gets the more vertices you have? Like, can you imagine doing this for a UPS delivery route? It is not effective to sit there and list every single possible route, because a single truck in a single day is visiting so many locations that could be your potential vertices, and there's so many edges that can be drawn in between. It's not optimal to sit there and do that kind of planning. So they need some other methods to use, and that's where your approximation methods come in. If you can get an approximation, that'll work. And in fact, UPS and USPS and FedEx and all them, they have the added kinks of looking at the little kinks in the system where it's like, what if we want to save time at a light and make all right turns and never have to worry about turning left or going straight? Turning right would definitely save time, because you can do that as long as you stop first. You can do that at a red light as long as nobody's coming. So they might want to incorporate these other factors. So sitting here and trying to do the brute force isn't necessarily the best way for them to do it. So we're going to look at 2 approximation methods. There's more, but we're only going to look at 2. That would make it's a lot faster and would make this a lot easier to think about. The first approximation method we're going to look at is called the nearest neighbor. And it's kind of what it sounds like. you start somewhere, you figure out where the nearest neighbor is, and you head there. Then once you're there at the nearest neighbor, you look around, you go, well, I'm ready to move on. And you go to the nearest neighbor from there. But you don't want to ever visit a point you've already been to until it's the very end and it's time to go home. So you just keep choosing whoever is going to be the shortest or smallest wait or the cheapest or whatever from your current location. Just making sure you never visit someplace twice until it's time to go home. And make sure you visit all your vertices before you go home. You don't want to skip a place. So going back to this graph, we're going to do that graph again, and we're going to look at nearest neighbor and how that would work for us. All right, so let me redraw the graph. A, B, C, D. And I used like a blue or something. All right, it was 10, 18, 14, 13, and then this was 15, and this was 16. Okay, so maybe I'll use a different color there. So starting again with A. I'm going to make sure I'm consistent. Is that what I did up here? Yeah, I started with A. So that's what we're going to do again here. So starting again with A, if I go A to B, that's 10. If I go A to C, that's 15. If I go A to D, that's 14. The nearest neighbor is B with 10. Okay, so I went there. I can't visit B ever again. Eventually I'm going to get back to A, but B's done. I'm at B. I like to think of myself as maybe a starving college student that's trying to hop across Europe. I only have just enough money to get to B, the shortest route. Once I'm at B, I don't want to spend more than I have to, so I'm going to look between C and D and see which one's the shortest. Well, from B to C is 18, while B to D is 16. So B to D it is. That's 16. Once I'm at D, I have no choice. I have to visit C before I go home. So I'm going to go to C, which is 13. Then I'm going to return home to A, which is 15. I'm going to add those up. 10 plus 16 plus 13 plus 15. I think it was 54. A, B, D, C, A. I have them all listed up here. A, B, D, C, A. Yeah, that was 54. And that turns out that was the cheapest route also with the brute force method. So this matches brute force in this case. But it didn't have to. You're going to have situations where your nearest neighbor is more than brute force. Your nearest neighbor should never be less than brute force. Brute force is your cheapest route, period. Nearest neighbor, and then the next approximation method will either be the same or a little more than whatever you found for brute force. Never cheaper, because you can't go cheaper than the cheapest. So in this case, it turns out that route also is a good approximate route. So that's nearest neighbor, approximate of the optimal solution. Maybe I'll do one more. Let's say I have a graph that looks like this. Let's do a 5-point one. Kind of like that'll be on your project. On your project, I ask you to do brute force. I ask you to do nearest neighbor. And then I ask you to do the cheapest link, which is the next one. Then I ask you to compare them. I want you to find the difference between brute force and nearest neighbor. And I want you to find the difference between brute force and cheapest link, so that you can see whether you indeed found the cheapest when you approximated. So that's part of the exercise. A lot of people miss that part. I don't know. I feel like it's pretty clear when it says find the difference. Subtract. All right, so we got these weights. These more complicated graphs start to get a little more confusing when you're trying to look at the weights. I'll try to draw these so it's really obvious what they go with. If you could do that for me too, that would be wonderful. So that when I'm grading it, I can tell exactly what your numbers go with. That would make a huge difference in the grading. Make me less cranky when I'm grading them. Okay, so there's your complete weighted graph. This one has 5 vertices. We're again going to start and end with A. We're not going to do the brute force right now. We're just going to do this nearest neighbor visit. So I like purple. So from A to B is 15, A to C is 13, A to D is 14, A to D is 25, I'm thinking ahead, sorry. A to E is 14. So we got 15, 13, 25, and 14. Your cheapest from here is to go to C, 13. Now that you're at C, you don't want to go back to A yet. Not time to go home yet. Still have some traveling to do. C to B is 17, C to E is 29, and C to D is 16. So C to D it is. It's only 16. All right, you can't visit C again. You can't go back to A yet. So D to B is 30, D to E is 12. So off to E you go. Then you do at this point have to visit B, because you have to go there before you go home. E to B is 27, and then you go back home. B to A is 15. So you add those up. I do not know if that is the optimal route in this example, but this is a good approximation, even if that's not the optimal one. Getting a total of 83. I wonder if that is correct. Let me do a quick check here. Well, A, C, D, E, B, A. Yep. 13, 16, 12, 27, and 15 gives you 83. All right, so that's nearest neighbor. Cheapest link's a little different. Cheapest link, we haven't selected any edges yet. We put all the vertices down. And we start putting down the cheapest edges. We're not going to worry about where home is right now. We're just trying to make a graph with the cheapest edges, or the smallest weights, or the least distance. And you're going to select edges of lowest weights without choosing one that causes you to close a circuit or causes you to have 3 edges at the same vertex. The vertex can have at most 2 edges coming out of it. You can't have a degree of 3. If an edge is going to be a problem, you skip it and go to the next lowest one. Then once you have a Hamilton circuit, you can add up the weights to see an approximation for the lowest cost. All right, so let's revisit the 4-point graph from earlier. Do that one first, and then we'll do the 5-point graph. Okay, our 4-point graph from earlier, we had A. I'm going to go ahead and redraw it just so we have it here for reference again, because we've moved past it since earlier. We had 10, 18, 14, 13, then we had 15 and 16. All right, so let me draw the vertices, and for now I'm going to pretend I'm not going to worry about home just yet. I can worry about it later. All I'm going to do is look at the edges and pick the cheapest, the one with the lowest weight. I have 10, 18, 15, 14, 16, and 13. 10's the lowest weight. All right, then after that, I can't use it anymore. I have 13, 14, 15, 16, and 18. 13's the next lowest weight. I can use it because I'm not making a circuit yet, and I don't have more than 2 edges coming out of any single vertex. All right, I got 14, 15, 16, 18 left. 14 is the next lowest, so I'll use it. I'm good. It's okay to have a degree of 2 at A and a degree of 2 at D. We just don't want to ever have a degree of 3. All right, and then I don't really have any choice. I've got to connect B and C at 18. And now I can address the fact that I want to start and end with A. So I could go either A to B to C to D back to A, or I could go A to D to C to B back to A. 28, 41, what, that's 55? A, B, yeah, up here. What was my brute force? Ah, my brute force was not that. My brute force was A, B, D, C, A. Because I noticed on when I did nearest neighbor, I got the same as the brute force. That was 54. So cheapest link did not get me the cheapest route, but it's a good enough approximation. So that is another way you could do it. So I got 55, and that's fine. That happens. It's not. I didn't do anything wrong. That is the answer. All right, what about that 5-point star? Let's do that one again, but let's do cheapest link. So I'll re-sketch the graph real quick so that we have it for reference. You know what? Let me draw it bigger, because when I draw it too small, it's so hard to see what I'm doing. All right, let's draw it really big. Hopefully I give myself enough space for the rest of this. All right. I had a 17, a 16, a 15, a 14, a 12. Then I had a 30. I had a 29. And I had a 20. Let's see, I had a 13 going this way. I had a 27 going this way. I had a 25 going this way. Is that all of them? Yeah. All right. So now cheapest link. Out of all those numbers, 17, 13, 30, 29, 16, 15, 27, 25, 14, and 12. Oh, let me label my vertices again so we have that for reference too. Sorry. So 12 is definitely the lowest there. The next lowest is 13 between C and A. The next lowest is 14 between A and E. That's fine still. I didn't make a circuit, and I don't have more than 2 out of one vertex. I have A and E have 2 now, but that's fine. I just don't want 3. Next after 14 is 15, and that would be this one. But I have to skip it, because then that would make A have 3, a degree of 3. I cannot use that. So skip that one. After 15, I have 16. Oh, I can't use C to D either at 16 because that would make a circuit. It's too early for a circuit. Way too early for that. We have that vertex B that still has to be used. I have a 17. Oh, 17 would be fine. That's between B and C. That one's fine. I did not make a circuit. And you know what? I'm kind of forced now to do B to D at 30. Don't really have a choice in the matter because I have to make sure now to complete a circuit. So it can be A to C to B to D to E back to A, or it can be A to E to D to B to C back to A. Complete reverse. So when you add those up, getting an 86 Let me double check that. Make sure I did my math correctly. ADBs, yep, 14 plus 12 plus 30 plus 17 plus 13 does equal 86. So there you go. If you were to do the brute force method with this particular graph, your cheapest route would not be at 86. Your cheapest route would actually end up coming out to a total of 74. A, B, C, D, E, A, or A, E, D, C, B, A, both come out to 74. That is your cheapest if you did brute force. So here's an example where you do not end up with the same number, and that's fine. That happens. On your project, you would then say, okay, my cheapest link was 86, minus my brute force was 74. That is a difference of 12. You know, so you're just kind of comparing and seeing how things turn out with approximations versus exact. All right, well, I think that covers everything that we were going to do for Hamilton paths, Hamilton circuits, etc. Yep, I'm out of slides. That's it. All right, so next video, I think we're going to be wrapping up graph theory, because in the next video we're going to be talking about trees, and that should be it for what we're covering in this unit. And trees will help. Once we talk about trees, you'll be able to finish up the project as well. That'll be the last piece of the project. All right, so thank you for joining me, and I look forward to seeing you again soon with more graph theory.